Now we're going to talk about exponential decay, still in 7.4. Researchers determined that the fossilized bone has 30% of its C14 or carbon-14 of a live bone. Estimate the age of the bone. Assume the half-life for carbon-14 is 5,730 years. This is not really calculus, this is basic pre-calc. So we know half-life, and we use the same formula you use for doubling time. The time for the half-life would be natural log of 2 divided by k, or if I solved it for k, it'd be natural log of 2 over t. And so we could say k is equal to the natural log of 2 for 5,730 years, and get our k 0.000121 per year. Okay, now we're trying to figure out when you have 30% left. So we're taking the same formula from before, P of t, P sub 0, e to the kt. And now P of 0 is the initial amount, which we don't know. We know this. Now it's radioactive decay, so it's negative. If it was growth, it would be positive. And then over here, I want 30% of that. And I find it interesting that 30% of that, you don't even have to know how much you had to start with. You can still figure out the time. Because you're going to divide by P sub 0, and that's gone. If I put a natural log through this, and so t is approximately natural log of 0.3 over negative 0.000121, which is 9,950, and this would be years. Okay, the next one is on pharmacokinetics. Pharmacokinetics. Interesting word. Okay, it says it describes the process by which drugs are assimilated by the body. So it's how fast your body is taking in, for example, acetaminophen or whatever other drug that you might be taking. And they've got the half-lives listed in your book on page 453 for many of the common ones: penicillin, amoxicillin, nicotine, morphine, tetracycline, digitalis, and phenobarbital. So, exponential decay function, same deal. P of t is equal to P sub 0 e to the negative kt. Only the book is using y sub 0s this time. The initial amount of the drug is 100 milligrams. Assume the half-life of the drug is 16 hours. Find the exponential decay function. So first thing I do is get the k. K is equal to the natural log of 2 over 16, which gives me 0.0433. So my formula, I want to use y's. P of t is equal to initial amount e to the negative 0.0433t. B, that was part A. Part B wants to know, oh, this was number 6, I didn't label it. How much time is required for the drug to reach 1% of the initial dose? 1% of 100 milligrams is 1 milligram. So the question is, when does this formula equal to 1? So if I divide by 100, that gives me 0.01. I put a natural log through, I get the natural log of 0.01. If I figure out t, I get natural log of 0.01 over negative 0.0433, 106 hours. So it takes more than 4 days for the drug to be reduced to 1%, the initial dose. That's a long time. All right. And Part C. If a second 100 milligram dose is given 12 hours after the first, how much time is required for the drug level to reach 1 milligram? Okay, so first thing I've got to find out is how much of it's left after 12 hours. So I'm going to figure out what P of 12 is. And it says 59.5 milligrams is still there. So the second 100 milligram dose that's given 12 hours after increases the drug. It's going to be now 159.5 because you still have 59.5 still in your system, and you take another 100. That's your new initial amount. So now the question is, when is 159.5 e to the negative 0.0433t, when is that equal to 1 milligram? Okay, so now I've got to solve this one for t. And if I do the same process I did, divide by the 159.5 and put a natural log through it, and find the natural log of 1 divided by 159.5. And then if I divide by that number, T is approximately 117.1 hours. Now, that doesn't mean 117.1 hours from the beginning. That's 117 hours after the second dose. And we waited 12 hours, so that means for 129 hours after the first dose. And that completes 7.0.